Good morning or good afternoon, wherever you are calling in from. This is Mark Richardson with Vibrant Technology, and I thank you all for joining us. I hope everybody is safe in wherever you are and you're healthy. Obviously, some trying times for all of us, so again, appreciate you taking some time out of your day to view our webinar here. Today, we're going to be talking about signal processing with MEscope ODS videos and really looking at some ways to clean up your videos to reduce some of the jitter, reduce some of the noise. I'm joined today by Dan Ambray from Full Spectrum Diagnostics, and Dan's going to be going through some tips that he's found that work for him and utilizing the MEscope software, some of the tools built into it. Previous 3 webinars, if you haven't had a chance, they are out on our website. You can go view those to view an introduction to MEscope ODS videos, along with a couple case studies that Dan has done. And we're going to continue making these, doing these webinars for the foreseeable future. And so we'll be doing some more case studies here in the next few weeks. So stay tuned. A couple of housekeeping notes. We are recording this video, so if you don't have a chance to view the whole thing, or you want to go back and view something you may have missed, you will get a link in your email sometime this afternoon with a recording to the webinar. In addition, if you have any questions, feel free to type your questions in the box on the right-hand side of your screen, and we'll get those questions answered for you at the tail end of the webinar. With that, let me hand things over to Dan, and we'll get started.
Hello, everybody. Thanks for coming out today. I know everybody's probably getting sick of webinars, but we have one that's a little more fun than the other ones out there. We're going to look at a piece of equipment that I did a test on a couple of weeks ago. It was a turbine generator system, direct driven through a gearbox. What you're looking at on the screen in the middle picture is the outboard bearing of the generator. And the picture just to the right of that is the foundation of the generator foot. And the little blue image in here is the Coronis 1.4 camera, which is right there. So kind of a peek into how we did the survey and so forth. We did that last week. There was, or last week or 2 weeks ago, can't remember. We did a little start to finish video on how to set up and what camera angles you need and what kind of data should be there and what to be looking for. Today, we're going to use some of that same footage, but we're going to look at how to clean it up a little bit. So we had some interesting problems with this machine. You can see the floor here, this little gasket. The slab is separate from the building foundation, and that slab was vibrating. So we turned the generator on at 1800 RPM. It was putting vibration through the whole structure, and the whole slab was vibrating at about 3 times the level it should have been. A lot of vertical vibration. So we're going to look at this in a little more detail, and we're going to walk through some different parameters that you might not have thought about, and a couple that we just put together this week. As it turns out, software, anything you can do manually, you can make it to do virtually with the software. And so we found a few more uses for it this year. Little definition, for those of you that don't know what ODS is, it's operating deflection shape. It's used a lot in industry on machinery that can't be shut down. So what we do is we have usually a reference transducer and then a roving transducer, and reference stays put. The roving one walks around the structure and collects data and a phase shift between the transducer that's moving and the transducer that's the reference. Now we have an amplitude and a phase, so at every point, and we can animate that and see how the whole structure is moving if we take enough measurements. Making that a little simpler, an MEscope ODS video is a high-speed video vibration analysis. Basically the same thing, except we don't have one roving transducer. We have simultaneously collected thousands of transducers. So every pixel on the screen potentially could be used in this analysis, which is about, at the highest resolution, about 1.3 million pixels. We use about 10% of that in our analysis, because it's amazing how much data that you have at 1.3 million pixels. So what we have is a high-speed analysis. The video clip is processed with what's called an optical flow algorithm. It enhances the displacement, rescales the amplitudes, and allows the user to see what your eye can't see, either because the event's too fast, the displacements are too small, or most of the time both, too fast and too small. So with that, why don't we get into this a little background and a little overview. We're going to talk about the histogram filter, and it's part of the wizard. It's the 5th step in the wizard. I am going to do the wizard live in a second here, just so for people that haven't seen it before, get an idea of what's going on. But the histogram filter is how we get rid of background noise and things that we're not interested in the video clip that might amplitude-wise take over the image. We also are going to talk about the camera itself. There's a buffer ring, a ring buffer inside that collects the data in kind of a virtual space, and it's a nice thing to know about. We just learned about it a few weeks ago, but it really helps minimize the jitter. There's an external trigger switch to the camera, a B and C switch. If I go back here, there's a little B and C plug in the side of the camera. We can use that to stop the video. And we don't use it, it doesn't do anything for the start of the video. And we're talking about pressing the button on the camera and actually getting physical motion, which will corrupt the image a little bit. So we're trying to get completely out of that. One would think, as I would, and did at the time, that the B and C connection, the external trigger, could start and stop the video, which it doesn't. It only stops the video. The reasoning is because it's designed for high-speed photography, and once you turn it on, you're waiting for that high-speed event to occur, and as soon as it occurs, you can turn the data stream off. So it's a little different function. Number 4 here is linear averaging and overlap processing. We have a new way of doing data now. Instead of taking a second or two of data, we take it until the buffer is completely full. Once the buffer's full, we can process it better. And it's amazing to see the averaging process. 1 average versus 8 is an order of magnitude better signal processing. And we'll show that to you as we move on. The last is a series of features, live cursor type features. The first is a magnitude and phase that we can get in the data. And currently it's just the Fourier spectrum magnitude and the phase itself with respect to the transducer, but we're trying to put it in an ODS FRF format. And if you're not familiar with that, that's a process that will get you amplitude and phase in the spectrum. And basically looking back at whatever reference point that we choose. So it's the basis of doing a normal ODS analysis. The other thing, orbit plots at selected points. We can select a point on the structure, have it create an amplified orbit plot. And this plot can give us a little better idea of the direction of what's going on in that piece of equipment. There's a band limiting process. We're extracting a discrete frequency out of the time waveform and putting it back. We'll talk about that transformation when we get there. And then differentiation and integration are a couple other mathematical functions of the software. Okay, software wizard. Little 5-step process. The first is you select what video you want, you adjust the video, and adjusting the brightness, the contrast, cropping, flicker rate, things like that if we have LED lights that are flickering. Number 2 is setting up the number of video frames and frame rate. We're looking for 1,057 frames per second is the maximum for the high resolution, and we really only want to process 1 second worth of data. We're going to do it in a different way than we did before, but if you've seen the previous webinars, but we'll show you the differences in that. We need to set a known distance, which is step 3, so that we have click the box and draw a line that's a known distance so that the software knows how far away from the structure it is at the focal length. The fourth is we select a point density. And remember, we're not taking 1.3 million points. We are processing the full density, the 1.3 million, but we're extrapolating that data to a grid framework on top of it, which is a little smaller in the 15 to 20,000 data points. And last, the filtering the data points with the histogram filter. And the histogram filter is the main basis. We're going to talk about it. First, I'm going to show you in the software, and then we're going to talk about it a little bit more and what it's used for and its limitations. And then we'll get on to some of the other points. Okay, let me jump out of here real quick. I'm going to go into the MEscope software. If you bear with me for a moment. Get my splash page. All right, we're going to create a new project. The next new project is project 47. We'll just save that. We have a new project 47 up here in the top bar. Under videos, we have a new ODS video. We can refilter it. We got some MEscope microphone recording and video type stuff that we'll talk about later. But in the first, we want a new ODS video. Here's our wizard. So the new video are 5 different pieces to the wizard. We're going to select a new video, and I have it on a external hard drive, and this is the one. Big video, 693 megabytes, 2¼ seconds long, which turns out to be too short, but we're going to revise that up quite a bit to 8 seconds. So we've selected the video. We can minimize flicker from the lighting. LED lighting's put out a flicker rate. The ones you buy to actually light up your housing, you can see some of the glare coming off it here, should be flicker free. If you buy your lights at Home Depot, it'll look like a strobe light's going off in your animations. So it's not real good. Regardlessly, I always check this box and it'll suppress some of that flicker from any plant LED lighting. Cropping, I can go in here and crop and get to a smaller section if I wish. I'm going to take the whole screen for this one. If I need to rotate the structure, if I have a vertical pump, a lot of times I'll turn it. You have to turn the camera to the long way. This is a good way to correct for that. Brightness, I can adjust it for dark and light, obviously, the brightness and the contrast, and same sort of deal. It'll bring out a little bit of what the color content in here is. So we got a video dimensions, 1024 by 1280, and we're going to talk about frames and duration next. So I hit the next button and I go into some of the other things we need to specify. This is, well, the frame rate, 1057 frames per second is what the camera was set for at the maximum resolution. So it needs to know that for the processing to see how many frames it has to process. So start frame to end frame, it's 8,730 frames in this set. Okay, I don't need that many. I need 1 second's worth. This is 8¼ seconds of time. Okay, so we started processing this a little better way. The first couple of times, and I'll show you a little later in the presentation, when you press the button, record button on the camera, you're basically putting a little pulse into the camera and it'll bounce on its tripod. And part of that whole camera motion will show up as the whole window shaking when you know it's not. In our case, it looks like the back wall back here is moving when it actually isn't. So we'll add a few seconds to what our normal capture would be, and we'll remove some of that problem, and I'll show you how. But anyway, let me play with this a little bit. I need 1 second of data, and down here I'm getting close. I need 58.78 there. Got 1 second of data at 1,057 frames per second, and I hit the next button. It asked me to set a distance, a known distance on here. I put a piece of a ruler tape from top to bottom on this end, and it was 8.75 inches. So I will make a rough estimate of that. There's my 8.75 and set my unit to inches, and we're good. Gives me a default point density, and I usually just go with that, and I think I will on this one. So 15,642 time waveforms it's going to extract out of that, and we're going to have every point's XY motion, and each one of those XY motions in the time domain is matched by frequency domain as well. So we have time waveforms and spectrum for every point in both X and Y directions on the screen here. So a lot of calculations going on. So I hit the extract time waveforms, and it starts its process, and I'm going to come back to that in a moment. I'm going to give you a little more lesson on what this next fifth phase of the wizard is going to be. It's the magnitude filter. I have my image, and it's covered with the grid of points, and I can't remember exactly, 26,368 points on this grid. Okay. When I use this magnitude filter, this is a histogram. What it's showing you, the blue side over here, many occurrences of low amplitude vibration. So basically the background noise. So maybe there's a structure in the background, another machine, anything moving in the background is pretty low amplitude vibration, okay? But you get a lot of it. So this is up to number of occurrences, over 1,200 occurrences. If I wanted to get rid of some of that, it would start removing these red points from my background. The green here, few occurrences of high amplitude vibration. So there's a couple of things. There's a couple of points where you see some glare. There's an electrical line in here. There's a little piece of piping on top there. There's a channel used for mounting instrumentation to right here, kind of hard to see, but you can see the slots in it. And there's a pressure gauge that all of these things are giving off high amplitude vibration, but just a few occurrences of it. So rotating shafts, blades, gears, piping, any LED glare is going to show up in the animation. Now you can do it without taking some of this out. All you'll see is if you have a really high vibration, it's going to dominate the response. And if you're looking for something and you have a glare that keeps bouncing around, it's very distracting. So you drop the amplitude down a little bit, and all of a sudden all the motion goes away. So this is a way of getting rid of the little technical problems of capturing video without losing any of the actual structural motion. Okay, so here's what happens. I start pulling out the first few bins of data down here. So remember, the highest one was 1,200 occurrences. So it's pulling points out all over the place. And so I do that a little bit on this side. It's many occurrences of low amplitude vibration, or it's eliminating the background noise. If I go the other end, it's pulling out all the little glare and things. So what I see in the background here is a couple of braided cables that we're moving around quite a bit. Here's the little light spots in that frame, or that bracket that was holding some instrumentation. So as it moves, you see a lot of motion in there. Piece of piping and this line electrical line that was coming up into the bearing housing. And there's something else up here. There's another electrical line that was on top of the bearing. What we're really after, we're trying to get all the points in this structure, not necessarily everywhere. Some of the flat spots will go away because it can't see any difference between the points next to it. So there's no XY information there. But all the edges are really important to get as far as the animation. It's going to extrapolate from there and give us a smooth response of what the whole structure is doing. But in order to, get rid of all this noise back here, based on the second thing, we'd have to really eliminate a lot of these peaks, and you start losing some of the data inside. So there's a happy medium in there somewhere. And if you play around with it enough, you'll get an idea. You can always go back and refilter. Okay, if you go and make these changes, let's say I make this change and I progress further and I create my data blocks, I can go back and refilter the system. This is what I want. So I got this the best that I could by eliminating all the high amplitude noise and the low amplitude noise. So I got rid of most of this wall response that wasn't moving. I got a nice outline all the way around the structure, and I'm going to get a good animation out of this. Okay. So I hit my create data blocks, and it'll start creating that thing, and it'll look something like this. So remember I said we get spectrum and we get time waveforms. This is the spectrum, one of the 26,000 that was generated. You can see very discrete peaks in here. This is a low frequency peak, and the whole generator sitting on the steel frame, and I believe that frame is twisting and bouncing. Okay, and it's about 700 CPM. So it's subsynchronous vibration below running speed. Running speed is 1800, which is on this side. There was also a gauge natural frequency. So the whole structure, it's moving here, it's bouncing up and down as a rigid body. Here, it's pretty fixed. No real motion at all, except for this pressure gauge is pitching up and down. The third peak, the biggest peak of all at 1800, the whole structure's bouncing in a little bit of vertical motion, a little bit of axial motion. But this is also bouncing again. So this is probably a natural frequency of this structure that's being excited by broadband noise, anything in the noise floor. It might be taking a little energy away from this, a peak 300 CPM higher. But there's probably just some lightly damped response here. Okay, one thing I wanted to see, and it does show up here, is it looks like these cinder blocks in the background are moving. I know the wall's not moving. I have a smooth wall down here, so there's no ridges for the optical flow algorithm to zero in on and show that motion. But it gets weirder than that. Remember I told you there's a boundary on the floor between the slab and the building structure. That slab that all this is mounted on, it's a generator, a gearbox, and a turbine, all in a big steel frame, and it's mounted on a slab that I believe is 1.5 feet thick, and it's mounted on pillars from the basement. So that whole slab structure is bouncing. And with it, my camera is bouncing, because this video was taken inside that barrier between the building and the slab. And so my camera's moving with the slab and with the generator and so forth. The wall's not moving, but it looks like it's moving because my camera's bouncing up and down. That's a hard one to get rid of. There's no real jitter control or anything like that that'll make that better. There is some manual method to eliminating that we'll get into next. So you get an idea, you can animate. This is operating deflection shape. Except it's in a video format instead of maybe 20 or 30 points that you'd normally do in a traditional accelerometer ODS analysis. This has 26,000 points. So you see really discrete motion. You can see, light changes in channel, in the little areas, the glare changes. There's pieces of this thing that are moving that you'd never be able to see with a transducer. This is that area. So little title here, manual methods. So when all else fails, we can clean up videos manually. I can't get rid of this because the camera's moving with the slab and it looks like the wall's distorted up and down. So I have an actual reason why this is there. What we can do is go in there and select points manually. So it's a grid work on the screen here, 26,000 grid points. The point spreadsheet inside of MEscope, I can go in, highlight an area I want to remove the links from, the video measurement links, go into the drop-down box and say delete links. So it's really easy to do. I did it in 3 blocks and got rid of all that background noise that was back here. Okay, so if I go back, this is before. You definitely, the wall looks like it's moving. Here's afterwards. Okay, so I've just delinked it from the camera motion. So it's one way of doing this. It's not the best. We were trying to figure out why it was doing that for quite a while, and it's like, oh, it's got to be moving, with the floor. So it made the most sense. So now I can see the absolute motion of the structure. And in fact, when we get in a minute, we're going to show some data from this location. While I was on site, I took an accelerometer and made a measurement on each bearing housing in X, Y, and Z directions. And I made that right here. And the data that showed up in the video analysis, it was in displacement, so we had to convert it to velocity. And it was almost identical to what we measured with an accelerometer. Pretty nice correlation. Okay. Couple of things. So we have camera-induced jitter problems. Camera settings, we have maximum resolution of 1280 by 1040. Camera speed at maximum resolution of 1057 frames per second. Minimum block time. We want to capture 1 second worth of data. Okay, 1 second is plenty of data to get a decent video animation. It's not enough data to get a clean waveform, okay? And there's a couple things going on. So camera and tripod transient motion at manual start and stop. Physically, when I press that button on the camera, I'm pushing it down and I'm actually moving the camera on the tripod, and then I'm letting off on that real quick, and it's like plucking a guitar string. I push it down to one direction and let it go, and boom, it bounces. You got a nice bounce, and a little smaller bounce, and a little smaller bounce, and then I hit the stop button. So in this case, it was a little 1.5 seconds or so, 1.6 seconds of data. So I get a pulse right here. It's kind of hidden by my arrow, but there's a different kind of transient pulse there. I bumped the camera a little bit harder than I should have, or out of phase with the pulse that was trying to decay. Regardless, I have a start and a stop recording transient, and this is my tripod motion. So I got to figure out how to make that better. So we get pulses and false motion in the video clip from this. Okay. Tripod natural frequency and broadband low frequency noise are usually a problem. When this occurs, time block shows 1.6 seconds of corrupted data. What I need is a longer time block so that the transients can settle out. 1 second, this is the key. 1 second is right for the analysis because all I need is 1 second of video, but not for the data capture. Data capture has to be a little more explicit, okay? Fortunately, there's a nice feature inside the Kronos camera. It will eliminate the start record jitter. It's a internal ring buffer, and this is how the data is stored. And they show it as a circle because it overwrites itself. So I have packets of data, each a second long, So when it gets to 8, the buffer's full, but as it goes further, it'll erase initial data. So if I press the button and I get a transient in 1 and it bleeds into 2, well, that'll be 9 and 10 going around again. It'll eliminate that data stream at that point. So it works really well as far as suppressing that input manual transient that you put in when you press the record button. What I found is simply recording 15 to 20 seconds of data, you eliminate the start transient. And what you have, you still have 8 seconds of data because that's all the buffer allows you to record, but it's clean. There's no low frequency wobbles in there. There's no big transient. It's just a nice smooth motion. Okay, that's what we're after. Okay, it relies on you to sit there and for 15 to 20 seconds after you press the button, but that's an easy thing to do. Okay, external B and C trigger. And I mentioned the B and C trigger. It cannot start the camera. It can only stop the camera. I think you'd probably be able to buy something that would do both, but in this case, it's more in the camera software that they never, it was a high-speed camera, so they don't really think it the same way. They don't think that you need any type of thing to start the camera because it's just going to run through its ring buffer, and all you need to do is stop it at the appropriate time after your high-frequency event has occurred, or high-speed event. So we can potentially have a record stop jitter response as well. This will take care of it. Okay, BNC external trigger. Now we have a total of 8 full seconds of usable data in the buffer ring. 1 second should be adequate for ODS videos. However, now we have the option of averaging the data for cleaner animations. Okay. This is an example of that. So this is data processing. You get a lot in the ODS video software. You get the power of MEscope. MEscope was born to do operating deflection shape analysis, and part of that is the data that you see. You don't just see a video, you see the data in the background. So every location, 26,000 measurements, I see 8 seconds worth of linear average data, and I see all the peaks that are in there. The difference between these two is here I took 1 second of data, or 1.5 seconds or so, and it might have been corrupted. I see some low frequency drift there, but I still see my 1500 CPM peak and my 1800 RPM peak in there. Those are the strongest peaks. But I missed all this. I missed 4 peaks out of 6 because they're overwhelmed in the low frequency end, and they're swept up by the noise floor in the high frequency end. Now I have a red line here. This is basically the baseline of the noise floor, and I left it in there for this one. They're both, it's about 0.5 mil of motion. This level is the linear averaged spectrum, and floor noise is down by 60%. Amazing drop off. This data looks so much better than this rough idea. It's 8 seconds of data, but this is all in the same frequency range. Everything is identical, except this is much better because it's highly averaged data. We can also do what's called overlap processing. So the process right now is set up for 8 linear averages because I have 8 seconds of data in the buffer. I can also do overlap processing where I take the first 1 second of data and do an FFT, and then each successive one, I'll take 10% of that window, or 1/10 of a second of new data, and process the 90% of the old data. So I can make a lot of averages out of that. So hundreds, maybe averages. Don't really need to. Based on this, you get a nice noise reduction by just 8 averages. But there's lots that you can do signal processing wise with that. Oh, speaking of which, better peak resolution, better phase resolution. So if we do this right with an ODS FRF function, we should be able to average the phase as well and get a nice nice total response and noise reduction. What does it do for you as far as the video? Not much. Okay, signal processing, that's great. Oh, sorry, that's my Alexa alarm. Alexa, be quiet. Oh, sorry about that. Everybody loves technical difficulties. So we have our 3 frequencies still that are in the data. We just don't see anything better in the animation because we can't see it visually. We can only see it in the data, the differences. This is live cursor amplification or amplitude and phase designation. And in fact, let me do this live. Well, I'll tell you what it is first. This is a time waveform animation at 1800 RPM. So we've extracted out a single frequency out of the data, FFT'd it from the time waveform, found a frequency, backed it out, and inverse FFT'd it back into the time domain. And what we put on here are a couple of, we selected a couple of points, and we can see the X and Y data on each point. Okay. And this is fluctuating quite a bit because it's a time waveform. So it's going from maximum positive to maximum negative and back and forth. This is a frequency animation at 1800. So same sort of idea, picked a couple of points, and we're showing some vibration. Of interest here is this is where we took the accelerometer measurement. And here's some data on that. But here's the amplitude information. So it's a little over 1 mil or 1/1000th of an inch of vertical response there. And this is in a peak format. So peak to peak vertically is just under 2 mils. If I convert that to velocity, it's 0.183 inches per second. The accelerometer measured data was 0.166 inches per second. And it's so pretty close correlation between those two. And there's little variations. You could be a little off on your set distance amplitudes. You could be a little off on your measurement response or where we took the data. So being off 10%, not that big a deal. We still resolve all the motion in the structure. Let me drop back, oops, into here. Here's my magnitude filter, my histogram, and doing it live always looks a little bit better than not. So let's crank this up. I'm trying to remove all that low frequency stuff, and it's getting there, but now I'm losing part of the data that I might want to keep when I go too far. And it's not coming off the wall as fast as it's coming off of here. So I wouldn't get a very good animation here if I took all my bins of data out that far. Here is about right. A couple of the rules of thumb. This is your proximity probe housing. So I have that fully covered. I'm covering this bearing housing cover all the way around the bearing itself, and I'm going to get some good data from this. And since the camera is moving, I'm going to have to manually remove some of these remnants in here. As far as the high end, the high large amplitude, but not many occurrences. Oops. You know, it starts to eliminate some things that I might want to keep, like around here. But this is not too bad of a filter. So if I create the data files, give it a new name, and I'll just default that. So it named my structure the same thing as the image file folder. Give the time waveform a name, and it calculates the 22,000 time waveforms, or 26,000, whatever it was. It'll calculate the Fourier spectrum of each one. So I'll get 26,000 Fourier spectrum. And then it'll drop me into animation mode. So it always starts up in the time waveform. So you're seeing all the frequencies at once when it's cycling through this, and it's sweeping through a time waveform. So you can see it doesn't look like motion that you'd expect. This is probably a little better demonstration of that motion, is at 1800. So it's showing me 1798. And I'm getting that same motion that we saw in some of the other animations. This is just doing it live. So this bar is interesting, this channel that connects electrical equipment. It's moving around. There's a braided cable with some wiring in it that's moving in the background here. This guy's flopping from the proximity probe cable. There's another cable coming in here, which I'm not sure what that is exactly, but it's a braided cable, it's electrical. And we do see the wall moving in the background. Okay, if I go put my cursor on anything, it shows me that amplitude and phase, so all over the structure. So in this case, nothing's really moving at all except for the mirror here. Okay. All right, there's a couple little hotkey scripts. I'm going to have to shut this down. I don't want to save anything. I'm going to open it back up to show you how these little hotkeys work. All right, this one, oh, webinar for 120. Oh, by the way, happy April Fool's Day. We should get that day off. Okay, I'm opening this up. This is the same project, the same piece of equipment, just processed a little bit differently. And I had some what's called little hotkeys or little script programs that are run in the background. The nice thing about this software as well is, there's a small group of guys who all are fantastic programmers. So if you can do anything manually, they can write a little script for it to do it, take all the manual effort out of it and do some really nice stuff. And it's not a big company, so they're always improving and changing. There's a new build to the software every week, usually on Friday, and everything's thoroughly tested. It's really nice, nice place to be associated with. This is a series of hotkeys. This one is select points. This is animate magnitude and phase. There's a band limit, which sets in the time waveform a band, and this is an extraction from the time waveform of a particular frequency, little routine that does that, and then it does the start animating command. This is the one we're going to talk about right now. I have my system up and running. I want to go into this one. Okay. All right, this is my spectrum that we just saw. Whoops. I can break that. So I have a spectrum and I have time waveforms. I can animate from either. Right now it's sweeping through the time waveform and you're seeing that motion. This is the spectrum, 1800 CPM. Oops. Why did that stop? There it goes. Got a little issue there. Sorry about that. Oops, now it's sweeping. I want it to stand still. There we go. Okay, there's my I must have a pause key on or something. Oh, well, sorry about that. I will have to go back to the PowerPoint. Sorry about that. But anyway, you can animate with the live cursor. You can select points. That was a little sub-program, and I just got it this morning, so I must have messed something up when I loaded it. 1800 RPM is the speed here, and you can see the amplitude's changing. This is walking through the time waveform, but also the phase is changing as well. So it gives you a little indication of what's going on in the X and Y directions. This is the frequency animation. So the phase shift between X and Y is 90 degrees, and that's what it's showing here. Ideally, what we'd like to see is one is a reference and one is the roving, and see what the phase shift between the two are. And we're working on that. So there's always some interesting things coming out. And I mentioned earlier, it was very close from the accelerometer measured data that we see here in the vertical direction, 0.166 inches per second. And the accelerometer measurement was very close to the video measurement. This is another feature. This is a live cursor orbit. The orbit in the XY plane, it gives you a little more insight in the overall motion. And it's a highly increased the volume on this quite a bit, so you could see the orbit even in the animation. It needed to be amplified a little bit. So we have bearing housing, and we have an overhung rotor. So you should have a little more cantilever motion out here, which you do, but it's showing me most of the motion is vertical. Kind of helpful for any location, but especially across a coupling. So this is the other bearing, the other generator bearing, couplings behind the guard. This is the gearbox housing. So if we were having some type of coupling misalignment, and they had a history of that in the past, they recently did an overhaul, you'd have out of phase motion across the coupling, which we don't see. We don't barely see any motion in the gearbox at all. And we see quite a bit of motion in the generator. So we know most of it's vertical, a little bit of thrusting, but a lot of the vibration is due to that, the whole floor being unstable a little bit. Okay, last of all, if you're interested, this whole webinar thing's taken hold of everybody. And a lot of my business is live training, but it turns out that I'm starting to put together a lot of webinar-based training. So one of the courses obviously is the MEscope ODS videos. It's a camera setup, camera lighting and logistics, MEscope ODS video software wizards, all the software hotkeys, how to install those, and then workbook guided examples. So my materials would be sent to the customer site. We'd sit down and do a 2-day or 3-day training, and we go through all kinds of different examples, and in the processing and in the animation and what have you. So it's a lot of the video software training, but then we'll show you a lot of features of the traditional ODS with accelerometers, so you can provide some clarity. And I've mentioned this in the other webinars, you can't always get a good video. You can get a couple of good shots, but you can't see all the way around it. You can't get to every direction that you want. Basically, just logistically in a plant, they're not set up that way for total access. So a lot of times you're going to have to go in anyway after you do the ODS videos. It'll give you a good idea of where to look and go do a traditional ODS to verify everything. I've missed things before because I've only been able to grab part of the machine, so I have to go in and see what the other side of the structure is doing. I also have a class that I've been teaching for years, and that's going to turn into a webinar class, I believe. So it's ODS and MEA, experimental modal analysis lecture and fundamentals. There's a workbook, so forth. And then any other, I already have live training on the internet, lots of different courses. So if you're interested in any of that, and I know a lot of people aren't in a position right now in this environment to purchase software, but when you get to that point, it's good to have some training to see what you need before you actually make the big purchase. So anything you have to add, Mark? Any questions?
No questions, no. You must have done a very thorough job.
All asleep, or they're just so happy they can't stand it.
If you have some questions after the webinar is completed, feel free to shoot those over. You can email Dan directly at modalguy@aol.com, or you can get a hold of us at webinars@vibetech.com if you got any questions, and we'll be sure to get those answered for you.
Anything would be welcome. It's amazing what we learn from people's questions. So if you have one, please let us know.
Absolutely. Be sure to check out our website as well. There's lots of good information on the vibetech.com website, including, like I mentioned before, the 3 previous ODS videos webinars. You can get a recording of those. With that, I guess we'll hang it up and stay tuned. We'll get another one of these spun up here in the next couple of weeks, and maybe we'll do another case study here in a couple of weeks. And yeah, hope everybody stays safe. Dan, anything else you want to
add? No, I'm good. Everybody stay healthy out there.
Stay healthy, everybody. Take care. We'll talk soon.